Hello, welcome to our webinar on Beating the Bandwidth Crunch produced by ARRIS. I'm Stuart Thompson, editor of Digital TV Europe, and I'm pleased to be joined today by Cornel Ciocirlan, Chief Technology Officer EMEA at ARRIS. First, a word about Digital TV Europe. We're a leading international publication and website covering digital media and pay TV across all delivery platforms, including whether traditional pay TV platforms such as cable, satellite, IPTV or digital terrestrial, as well as over-the-top internet-delivered TV services. We've been providing independent information, research and analysis for the industry for 30 years, and we're widely used as a key information source by senior executives and management. ARRIS, as many of you will know, is a global innovator in IP video and broadband technology. It has been a pioneer in digital TV, delivered the first wireless broadband gateway, and is a pioneer also in developing the standards and pathways for personalized Ultra HD, multiscreen and cloud services. The topic of this webinar is the bandwidth crunch. Now, IP video and cloud-based services are likely to lead to massive growth in demand for bandwidth, and service providers are going to have to rise to the challenge. Cornel is going to look at how some of those service providers can plan ahead and outline the impact of some of the technologies at their disposal. Before handing over to Cornel, I'd just like to run through the procedure for asking questions at the end. After the presentation is concluded, we'll open for questions, and if you please type your questions into the box on this page, our speaker will provide the answers. The session's intended to be interactive, and we very much encourage you to place as many questions as occur to you. So with that, it's my great pleasure to introduce ARRIS's Cornel Ciocirlan.
Okay, thank you, Stuart, for the introduction. Let's go right into it, because I think we're going to be a little bit pressed for time, and we would like to leave some Q&A, some time for Q&A at the end. So over the last few decades, really, the internet has been since the internet has been commercialized, we've seen a tremendous growth in internet traffic. Bandwidth growth has continued at a rate of about 50% per year, and really what has happened is we've moved all sorts of media from physical format to digital and to online. In the 1990s decades, we had the migration from letter to email, and the communication was really revolutionized by that. In the 2000 decade, we've moved music and pictures in digital form and then online. And we're now living through the 2010 decade where video is moving online in the form of streaming video and can be accessed on a variety of devices that are always with us. What will happen in the next decade to continue to drive that? There are various schools of thought about this. Some people think that video will continue to drive the growth, and that will experience immersive video and video conferencing, very high-resolution video conferencing. Machine-to-machine communication, according to others, is going to be a significant growth driver, and various types of cloud applications for healthcare and things like that are also thought of as being potential growth drivers or killer apps in the future. The reality is we don't really know what will continue to drive the growth to the level that we have seen so far. One example is if we look at the video streaming as a growth driver, we really have to ask ourselves, are we ever going to stream more than something like 200, 250 megabits per second per home? Even with a very high resolution video screen, what we call a wall screen, 8K resolution, 120 frames per second, and that's basically constantly streaming something, a video stream into the home. We probably won't need more than 160 megabits per second of bandwidth for that one screen. And then even if you consider another couple of streams in the home, 3 or 4 4K 60 streams going into the home, that's probably another 80 megabit per second altogether. So that is a lot of capacity, and especially if it's constantly being streamed into the home. However, it's not the 1 gigabit per second type of bandwidth that people are talking about. And so the question is video going to be the growth driver, or will there be something else, or will the growth subside and maybe reduce to a bit slower rate? As we're going to see on the next slide, here we have basically two possible scenarios. We're really at the crossroads in 2015, and one possible scenario is the 50% growth will continue and unabated, and there will be new applications being invented, and that those applications will continue to drive the growth at the same rate as to date. The other scenario is growth subsides and the growth rate reduces to something like 30% year on year. And it may not sound like much, but if you compound these growth rates over a couple of years, the results are pretty drastically different. So before we go into the detail on that, let's discuss a little bit how capacity planning works in a DOCSIS or in any network really, but especially in a DOCSIS network because we have in a cable network because we have a shared medium. Operators are always have to keep an eye on two things. One is the top tier of speed that they offer their subscriber. Let's call that the offered bandwidth, otherwise known as Tmax in some cases. And the other one is the total consumption, the total bandwidth that subscribers consume in that serving group. You have sometimes 200 subscribers sharing a single pipe, and they generate a certain baseline bandwidth consumption. And those two factors are really what drive capacity planning and the capacity that operators are deploying into the networks. If we look at this picture on the left side, you have the two components. In this example, we have a 200 megabits per second offered bandwidth. That's the tier of service that the operator is offering to their subscribers. And we also have an aggregate average bandwidth per serving group of 150 megabits per second. In order to support such a service, the operator would typically deploy a 400 megabits per second pipe into that serving group. That would be 8 DOCSIS 3.0 channels. And really the delta between the 150 megabits that you see on the left side, which is the baseline consumption, and the top, the maximum amount of bandwidth available in the serving group, we call that the burst reserve. And the burst reserve is always has to be higher than the Tmax. Think about that as we need to allow any one of those subscribers that are part of the baseline consumption to burst up to their maximum speed tier. Usually those bursts are very short duration in time, but they need to be given that level of service. So what happens if we look at the next few years in growth, both in the baseline 50% growth as well as the growth in tier of service? Here I've considered the baseline growth from a 2015 level of about 600 kilobits per second, all the way to 2020. And then what happens to the tier of service if we consider the tier of service growing at a relatively similar rate? You can see here that the amount of DOCSIS channels that are deployed very quickly goes to 16 in 2016. In this case, to support 500 megabits per second service, you would need at least 16 DOCSIS 3.0 channels. And then once operators move to 1 gigabit per second in 2017, they would need to deploy at least 28 DOCSIS 3.0 channels. And then quickly after that, they basically reach the limit of 32 DOCSIS 3.0 channels. There are no plans in the cable labs. There are no plans at cable labs to introduce modems that support more than 32 DOCSIS 3.0 channels. So because of that, most operators are going to stop and cap the DOCSIS 3.0, the number of DOCSIS 3.0 channels deployed in their network to something like to a maximum of 32. Some are talking about even 24 or 28. But certainly, we don't see any operator planning to deploy more than 32 DOCSIS 3.0 channels, especially in Europe, where each channel has a little bit more bandwidth than in the US. If the growth rate drops to 30%, that's a possible scenario that some operators certainly in the last 1.5 years are indicated they think it becomes likely. They've seen a slight reduction in growth, and certainly in the mature markets like Western Europe and the United States, where the penetration of broadband services is almost the highest as it can be, the growth rate, bandwidth growth rate, may reduce to something like 30%. In this case, we see a dramatically different picture emerging. We see that certainly both the average utilization as well as the top speed tier will grow slower, and even all the way to 2020, we see that operators will be able to live within a DOCSIS 3.0 deployment without a fundamental need to migrate to DOCSIS 3.1. They're not breaking the limits of DOCSIS 3.0 with a maximum of 32 channels. Even in 2020, the burst reserve, the bandwidth burst reserve percentage here, you see it's 65% of the bandwidth deployed in the serving group is reserved for burst. So that should ensure a very good quality of service, even with the DOCSIS 3.0 only deployment. One thing that influences capacity planning as well, and actually drives the investment in the network, is the reduction in node size, in serving group size. Basically, as operators are looking at are trying to cope with bandwidth growth, one method is obviously to increase the number of DOCSIS channels, but that helps in some cases up to a certain point. Beyond that, you need to really start looking at reducing the number of subscribers that share the same pipe, and that's called a node split in cable terminology. Splitting a node is something that operators are doing all the time. There's a background level of node splits as capacity bandwidth growth increases and people demand more and more capacity. Operators are splitting nodes in order to keep up with the growth. One interesting consequence that we see is as the node size reduces and there are fewer and fewer subscribers sharing the same node capacity, the importance of the maximum offered tier of service in that capacity formula becomes more and more significant, to the point where the offered bandwidth is the dominant factor in that capacity formula as the nodes become smaller. Another way of looking at this, we can see on the next slide, is if we calculate how many months we see, how many months is a node split buying the operator. Once they've reached, let's say, the limit of capacity on that node, and they have to split the serving group, how many months does that buy them until they have to split again? Based everything else being equal, and assuming 50% average growth rate. And as you can see here, as you go to smaller and smaller nodes, the benefit is diminishing as well, to a point where when you go to 64 subscribers per node, and you go from 64 to 32, you really only gain 2.7 months before you need to split again. So now, granted, very few operators are at that level today. Most of them are somewhere at 512 subscribers per node. So we still have a few years of node splits ahead of us, but at some point node splits will cease to be a useful tool in the arsenal that cable operators can deploy to keep up with bandwidth growth. They will have to focus on other techniques like spectrum expansion and DOCSIS 3.1 and things like remote gadgets. We talked earlier about deploying 1 gigabit per second with DOCSIS 3.0 and whether it is feasible or not. It is feasible. This is one picture showing how operators could deploy a CMTS infrastructure with DOCSIS 3.0 channels and manage an existing population of cable modems within a large amount of DOCSIS 3.0 downstream channels, a population of existing modems, very diverse modems with 4 downstream channels, modems with 8, with 24 downstream channels, and modems with 32 downstream channels can coexist on the same serving group. And operators can offer the top tier of service to the cable modem with 32 channels, and the other ones can get the tier of service that their cable modem allows them to get. So this is going to become a typical model over the next few years. As some operators will deploy 1 gigabit per second with DOCSIS 3.0 before switching to DOCSIS 3.1. They will be deploying 24 channel and 32 channel modems within a maximum serving group capacity of 32 DOCSIS 3.0 channels. One interesting consequence of this discussion is that it becomes very important for the operator to make a good choice of CMTS to be able to support the growth in number of channels, going from 8 to 12, as we've seen today, to 32 channels. That's a tremendous amount of growth in the number of channels. That is why operators have essentially standardized on deploying CCAP technology over the last 2-3 years since CCAP technology has become available, because this technology does allow very easy growth in the number of channels per port with essentially a license-based software upgrade. You can grow the number of channels per port from 8 to 12 to 24 to 32 without going out and replacing anything in the field. So the key takeaways from the discussion so far: the growth rate is key. If the growth rate is 50% or 30%, that will have a fundamental impact on the operator strategy. So operators have to keep a very close eye on the bandwidth growth rate and react quickly if the growth rate diminishes. 500 megabit service can be launched with DOCSIS 3 with 24 channel modems. Even 1 gigabit service can be launched with DOCSIS 3.0. 32 channel modems allow that. And obviously, operators need to find the spectrum to deploy 32 DOCSIS 3.0 channels per serving group. And I think some operators may decide to cap the amount of DOCSIS 3 channels at 24 and roll out 1 gigabit service with DOCSIS 3.1. It will really be dependent on the individual operator's strategy and growth rate. What is certain is that speeds above 1 gigabit per second will be offered with DOCSIS 3.1 only. And in order for operators to prepare themselves for that, they will be over the next 3-4 years. All operators will deploy DOCSIS 3.1 strategy. And the other takeaway is that CMTS per port density is very important. CCAP platforms are needed in order to reach the 32 Annex A narrowcast single carrier comms per connector, and that is why the CMTS market has been revolutionized over the last 2 years or so by the introduction of CCAP. Let's go a little bit into more detail on DOCSIS 3.1. Not too much given the available time, but just to give you an idea of what kind of capability DOCSIS 3.1 brings to cable networks. In a typical deployment, you can see here in the fifth column, full spectrum DOCSIS 3.1 can theoretically support something like 9 or 10 gigabits per second in the downstream direction, and anywhere between 500 megabits and 1.25 gigabits per second in the upstream direction. This is very competitive, and essentially DOCSIS 3.1 is able to future-proof cable networks for the foreseeable future. As you've seen, certainly for the next 3, 4, 5 years, even DOCSIS 3.0 is future-proof enough. DOCSIS 3.1 probably adds another decade to the life of cable networks easily. So we're very confident that DOCSIS 3.1 technology will allow cable operators to continue to extract value out of their networks going forward. How will they do that? One essential step in the rollout of DOCSIS 3.1, we've talked about earlier about the fact that node splits will reach the end of their useful life in the next few years as they become small enough. Splitting nodes becomes essentially useless. So operators will have to deploy another tool in their arsenal, which is to expand the spectrum to migrate from 860 megahertz, which is where most people are today, to 1 gigabit per second or 1.2 gigabits per second in the downstream. And also in the upstream direction, as capacity requirements grow, operators will be moving from 65 to 85, introducing additional upstream spectrum in the 65-85 part of the spectrum. And eventually, somewhere in the next, let's say, 10 years or something like that, operators will reach an end goal of 5 to 204 megahertz in the upstream, which gives them about 1.25 gigabits of capacity in the upstream direction, and 258 to 1.2 gigahertz in the downstream, which gives them that 9 gigabits per second that we were talking about earlier. Clearly future-proofing the DOCSIS network and the cable network for the foreseeable future. How will operators go about reallocating spectrum to introduce DOCSIS 3.1? This is in the vertical axis. You see the spectrum. It's the megahertz essentially from 0 to 1.2, and in the horizontal direction you have time. And what you see here is on the left side, you start from today's situation where you basically have mostly 3 types of services: analog video, legacy video QAM, DVB-C, digital video QAMs, and DOCSIS as the main components, the main services that are present on the cable network today. What operators will be doing once the number of DOCSIS 3.0 channels reaches a number like 24 or 32, they will be capping the DOCSIS 3 channels, and at some point they will be introducing DOCSIS 3.1. Whether that's introduced in the downstream or in the upstream first, it's debatable. Some operators are driven more by upstream capacity requirements than downstream, but most people, for the I would say 80% of operators out there, DOCSIS 3.1 downstream introduction is likely going to be more a higher priority than upstream introduction. And once DOCSIS 3.1 is introduced and DOCSIS 3.0 is capped, there's another thing that will drive the evolution of spectrum mix, which is the migration to video over IP. Already we see Netflix, for example, has caused a reduction in TV viewing time by 12% in the last year in the US. That news came a couple of days ago. That's very interesting news. So clearly what operators will be doing and will have to do is to evolve their user experience to be more flexible and to start competing with alternative operators like Netflix, like Amazon, like Google. and they will have to strengthen their IPTV offering, migrating traditional video services, moving away from legacy analog video, moving to some extent away from legacy video QAM, and into this new world of streamed video service, which will continue to drive bandwidth utilization, and the spectrum mix will change up until the end game, but probably we're 10, 15 years away from that. The end game will be a full DOCSIS 3.1 spectrum, both in the downstream direction and in the upstream direction. Just a few words on distributed access architectures. What are the future concerns that operators are considering when they think about when they consider distributed access architectures? One is the head-end space and power, and it's a key concern because if operators are splitting nodes and will continue to split nodes, let's say from 1,000 homes passed per node to 100 homes passed per node, and that's probably where they will stop. But even this 1,000 to 100 migration results in a significant increase, a 10 times increase in the number of serving groups. That may cause cable head-ends to run out of space or to run out of power consumption. It will also increase the amount of fibers or wavelengths coming out of the cable head-ends, and that may cause problems, and operators are trying to avoid that. The other one is nonlinear optical noise, because we're introducing more wavelengths to support these increased amounts of serving groups. And the fiber lengths are longer and longer because the nodes are closer and closer to the edge of the network, to the subscriber. We're starting to encounter more and more nonlinear optical noise phenomena that are reducing the overall capacity of the network. If we look at the space problem, there's still a lot of gains to be, or savings to be realized in terms of space in the head-ends and even power consumption as well, because really CCAPs have to date been deployed as pure CMTSs. Very few operators have gone through the effort to collapse their existing edge QAM infrastructure, broadcast, RF combining, and into the CCAP platform. That, honestly speaking, that saving, that gain is still out there to be realized, and operators will start to really deploy CCAP platforms as converged platforms in the next 2 years. There's at least 60% reduction in rack space utilization that can be easily extracted out of that. There's a reduction in power consumption as those older generation edge QAMs are decommissioned. So we think that clearly the space-saving aspects of CCAP have still to be realized, and there's more to come in terms of CCAP technology evolution in the next 5 to 6 years. So our view is that space and power likely will not be such a big problem. The existing evolution in CMTS technology and CCAP technology will be able to support the increase in number of serving groups. Having said that, let's take a look at what the impact of where the gain is most significant if we deploy a remote gadget versus a traditional architecture. In a short amplifier cascade, just to avoid complicating the problem, what we're showing here is the SNR gain that an operator can extract, depending on the number of wavelengths that he's deploying and the optical link distance. So, if an operator migrates from a traditional network architecture to a remote gadget, remote PHY, or remote CCAP network architecture, and that operator is in the top. The network architecture for the operator is in the top right corner with between 8 and 16 or more wavelengths per fiber and 60 to 80 kilometer fiber runs, he can gain quite a bit of improvement in the capacity of the network because he can avoid nonlinear optical noise and things like that. So now in this picture we haven't included the impact of the home network, and it's very interesting to see what happens when we start to include that. In the next slide, essentially, once we include the impact of the home network, the benefits of remote PHY are pretty much neutralized because in most cases, the home network is a much noisier, much worse contributor to overall performance degradation in the cable network than the actual network itself. So we're ending up in a situation where even if we would be able to extract a lot of benefits out of remote PHY, if we keep the currently existing home network, we're going to face a significant problem. So how do we solve that? Well, the solution is to create this point of entry gateways into the home, and that has to be part of an operator strategy as they move into the new world of DOCSIS 3.1 and remote PHY. ARRIS obviously is planning both remote PHY and remote CCAP products. We are going to develop both platforms, both types of platforms, in the next few years, helping operators to evolve their network into this new world. At the same time, we're going to have to talk a little bit about the home network, because as we've seen, it is a fundamental restructuring. The home network is fundamental to being able to extract the benefits of remote PHY. Here are a few questions that operators will need to answer, and if they want to decide if and where remote PHY architectures can be used. Remote PHY will not apply, or remote gadgets will not apply to the entire operator's network. Typically, they apply to targeted areas where that signal-to-noise ratio benefit that we saw earlier is most important. Many operators, certainly in Europe, are more towards the left of that graph that we've looked at earlier. So they're even in the best case, they probably won't be able to extract more than 3 to 6 to 9 dB of SNR benefit. But in order for operators to make a decision, they really have to look at their network architecture and look at the need to multiplex many lambdas on a fiber. The length of the optical links, what's the distribution of optical link length? They have to look at that across the network and decide for the long links and where they have many wavelengths per fiber, they will have to deploy remote PHY or remote gadgets technology. Are they running out of head-end hub space, power, cooling capacity? That really is a very important question, but that's coupled to the CCAP evolution and the increased density of the new CCAP products. Do they have many small head-ends for operators with small head-ends, less than 10, 15 serving groups? Remote gadgets may make sense. They can deploy one of these remote CCAPs in a small head-end and support the 10 to 15 serving groups in the head-end. And the desire to reduce optical transceiver costs. Ethernet is obviously a much widely deployed type of technology, and the cost of an Ethernet optical link are certainly lower and will continue to be lower than the cost of an analog optical link as is currently used in HFC networks. Also, do they want to take advantage of the opportunity to change to a future optical node technology when the DOCSIS 3.1 mid-split starts to be deployed in nodes, and when these new nodes with full spectrum output downstream as well as upstream appear? Operators have let's say, visibility to an end of investment into the node platform certainly until the next round of expansion, spectrum expansion happens, but that's probably 20 years away at this point from what we see. Just briefly touching on 1 gigabit per second in the home, we've seen the importance of the home network as a significant contributor to signal degradation in cable networks. So there are really, in terms of DOCSIS 3.1 silicon availability, just to give you an idea there, we see the first silicon being available in the first half of 2015, depending on silicon vendors. And Cable Labs certification will happen sometime in Q4, will start in Q4 this year. And production ramp for DOCSIS 3.1 gateways will likely start somewhere in the middle of 2016. But over the course of the next few months, we will be engaged in a lot of early testing with the operators to qualify and validate the benefits of DOCSIS 3.1 technology and refine the technology ahead of field deployment. How much does it cost? The CPE cost is obviously one of the most important costs that are driving the investment, the CapEx investment for operator. Well, clearly, if we look at cost per megabit per second, which is what we need to look at in order to express the investment required for a given capacity, we see that the price per megabit in the CPE keeps dropping. With the generation 3.5, let's say 32 by 8 DOCSIS 3.0 channel modems, you get a significant cost reduction versus DOCSIS 3 24 or 8 by 4 channel modems. And then when we move to DOCSIS 3.1, it's really a fundamental shift. The cost per megabit per second with these 5 gigabits per second gateways drops to about 32% of today's value. So this really helps operators maintain a flat capex profile while being able to invest in new technology and to deploy ever growing amounts of bandwidth and capacity. There are really two architectures emerging. We've seen earlier how the home network is a significant problem because it contributes a lot of noise and therefore it reduces the total performance, the total overall performance that the cable network can achieve. The two architectures both rely on having this concept of a one gateway into the home that is the terminating point for the cable network, and from that entry point into the home, the distribution of the signals, whether they are video or just internet traffic, happens over an IP in-home IP network. The traditional option is the one where you have an all-in-one wireless gateway located typically where the user wants it to be located. The operator doesn't really have a choice there. And the second emerging architecture is this network termination unit concept, where the DOCSIS 3.1 device is placed somewhere at the entry into the home in order to avoid any of the in-home cabling. And everything in the home is done over an in-home IP network. There's a wireless bridge that is connected somewhere in the home, and that wireless bridge is the one that really ensures Wi-Fi connectivity. The benefit is that the NTU, the network termination unit, is at the entry point to the home. Therefore, the operator can avoid all the noise and the problems that are coming from the home network. And the wireless bridge, the wireless access point, can also be placed in an optimal position to ensure the best Wi-Fi coverage in the home. And combined with the previous architecture, the concept of an in-home network really becomes fundamental, right? We've seen certainly in the second case, but even in the first case, the need for wireless extenders is becoming obvious. More and more people depend on Wi-Fi, and Wi-Fi is high-quality Wi-Fi, gigabit level Wi-Fi. The ability to deliver that 1 gigabit through the home, not just into the home, requires the use of repeaters to ensure the best signal, Wi-Fi signal everywhere into the home. So in order to extend the Wi-Fi coverage, there are two things needed: a number of extenders, Wi-Fi extenders, certainly in larger homes, but also a home network, a high-capacity home network, a gigabit-class home network that can be used almost as an in-home backbone to ensure that the Wi-Fi, the traffic passes over a reliable and high-bandwidth network. ARRIS obviously has been using MoCA so far. We've been using MoCA to great success in the US as an in-home network. And as we go towards the need for gigabit home networks, we're working on G.hn as well. We will have a range of products, G.hn products, that ensure connectivity through the home, and we will make sure that any device in the home can deliver, can receive 1 gigabit per second signals wherever they are. And finally, before I hand it over back to Stuart, the future, certainly in the home, will be an extremely high-density Wi-Fi network and very dense antenna arrays that are capable of offering tremendous amount of capacity, gigabit plus types of levels of capacity into the home. This is an example. It's a test lab, but in some parts of the world, the future is already here. In some labs out there, the future is already here, and it's just a matter of time before we all get a chance to see it. Thanks everybody for listening, and I'd like to hand it back over to Stuart.
So thanks to Cornel for a very informative, detailed and stimulating presentation. As I mentioned earlier, we'll now open for Q&A. Please note there is no audio element to the Q&A. All you need to do is type your question into the box and answers will appear in the comment stream. Now finally, I'd like to thank you all for listening, and I hope you found the presentation interesting, informative and enjoyable.